Alright folks, welcome back. Hey, before we begin another rate law problem, let me give you guys a quick algebra lesson. Most of you probably already know this, and it's not going to be too horribly difficult for you, but I just want to make sure. Let's say we have this proportionality. A is proportional to B to the 0 power. We'll put some numbers in there. Let's say B is 1 to the 0 power. Alright, if that were the case, what would A be? Well, A would be equal to 1. All right. Let's say we double B. So we go from 1 to 2. So 2 to the 0 power. What's A now? Well, it's also 1. It hasn't changed. Let's say we triple it. We go from 1 to 3 to the 0 power. What's A again? That's right. A is still 1. Anything to the 0 power is 1. It doesn't change. So when I double the amount of B, it will make the amount of A unchanged. And when I triple the amount of B, it will make the amount of A unchanged. So no matter what I do to B, it has no effect on A. And we call those zero-order reactants when we do rate law. And we'll see a few of those. Now, what if B is to the first power? Let's put some numbers in there. Let's say B is 1 to the first power. A would be 1, of course. Let's double B. Let's put B to the second power. Or let's double B, sorry. So now it's 2 to the first power. A is now 2. Let's triple B. So we'll go from 1 to 3 to the first power. A is now 3. What if I 7 tupled B? 7 to the first power, A would be 7. So whatever I do to B, the exact same thing happens to A. We call that a direct proportionality, as you know. But when we do rate laws, we call these first-order reactants. So doubling B, remember, will double A. Tripling B will triple A. Whatever I do to B, it will have the exact same effect on A. And finally, for rate law, the last one we have to worry about is squared or second order. So let's make B 1, and we'll square it. Of course, A is 1. Let's double B. So we'll go from 1 to 2 squared, and now A is 4. So I doubled B, and A quadrupled, didn't it? All right, let's triple it. So we'll go from 1 to 3 squared, and now A would be 9. So when I tripled B, A 9 tupled? Yeah, 9 times. What if I quadrupled B? Yeah, you'd expect A to go up 16 times. So whatever I do to B, you square it, and that tells you what effect that will have on A. When that happens, we call those second-order reactants. Now, just a reminder, proportionality signs can be replaced with equal sign, so long as we add a proportionality constant in the equation, which we have when we do rate law problems. Remember, rate laws always begin with R equals K, and then for our generic reaction, we have reactant A to some power of M, reactant B to some power of N. We could even have 3 reactants, reactant C to some power of O, and so on. Okay? All right, well, let's go ahead and let's try another problem. Example 3 in your notes is a reaction between hydrogen gas and nitrogen monoxide. We're forming water vapor and nitrogen gas. And I'm going to conduct 7 different experiments where I'm going to vary the concentrations of my reactants, NO and H2. And I'm going to measure the rate. This is actually a mistake. We're measuring the rate in molarity units of change per minute. So in my first experiment, the concentration of NO is 6 moles per liter, and H2 is 1 mole per liter. We put that in a cylinder, and we measure the concentration change. Don't worry about how or why, but we get it to be 20 molarity units per minute. All right, in the second experiment, I keep the concentration of NO constant. We don't change that. Still 6 moles per liter, but I've doubled the concentration of H2. When I do that, my rate doubled. Isn't that interesting? When I doubled H2, the rate doubled. Let me look at the third experiment. In the third experiment, NO is still 6.00. So between the first and the third experiment, NO concentration didn't change. But between the first and the third experiment, the H2 concentration tripled. What did the rate do between the first and the third? that also tripled. It seems to me that whatever I do to the concentration of H2, the same thing happens to the rate. Do you remember what we call that order? That's right. We call that a first order reactant. All right, let's clean this up a little bit, and let's see if we can find the order with respect to NO. So for NO, what experiments are we going to use? Yeah, let's take a look at experiment 4 and 5, where I keep the concentration of H2 now constant, and I double the concentration of NO. Now when I do that, my rate goes from 3 to 12 molarity units per minute. It quadruples. So I doubled NO without changing the H2, and my rate quadrupled. All right, let's see what happens when I triple NO. So I go from 1 to 3. I tripled NO, and H2 is still kept constant. My rate went from 3 to 27 molarity units per minute. It nine-tupled. It looks like whatever I do to NO and I square it, I get what happens to the rate. So 2 squared is 4, 3 squared is 9. So that means NO is what's called a second order reactant. So now I can write my rate law. R equals K times the concentration of H2 to the first power and NO to the second power. We got those exponents, kiddos, by looking at this experimental data. Now, let's go ahead and calculate the value of K. So K would be equal to R over H2 concentration to the first power and NO concentration squared. Remember how we do that? That's right, I like to use the first experiment. So let me clean some of this up a little bit so we can see it better. And we'll highlight the first experiment's data. So I know the rate and the concentration of NO and H2. So K equals the rate during that experiment, which is 20 molarity units per minute, divided by H2 concentration, which is 1.00 molarity units, divided by NO concentration, which is 6.00 molarity units, and we're squaring that because remember it's second order. Looks like those molarity units cancel out, and we have 1 over minute molarity units squared as my unit. Let's see what the numerical value of my rate constant is. So we have 20 divided by 1 divided by 6 squared, which is 36. Looks like, let's call that 20 with a decimal at the end to give me two significant figures. I have a rate constant of 0.56, 1 over minute molarity units squared. So now that we have our rate constant, we should be able to calculate the rate during experiment 7. Do you notice we don't have the rate during experiment 7, but we do have the concentration of NO and H2. So let's do that. R equals K, which is 0.56, 1 over minute molarity units squared, times H2 concentration during that experiment, which is 3.78 molarity units, times NO concentration squared, which is 2.45. So we have 2.45 molarity units, and we're going to square that. So it looks like my molarity units squared cancel out, and I have molarity units per minute again as my unit, which is perfect because that's a rate unit. So let's do the math. We have 0.56, that's our rate constant, times 3.78 times, I'm going to use my parentheses key here, kiddos, 2.45 caret key squared, close parentheses, and I get 13 molarity units per minute for experiment number 7. So I was able to find that rate without having to actually do the experiment, okay, because I knew the rate law. Alrighty? Yeah, I know. You want to try one on your own, so let's go for it. Why don't you take a minute and try doing example 4 without my help? Okay, now actually pause the video and try this, kiddos, and then come back and see how I did it. We'll see if our answers match. Okay? See you in just a sec. All right, welcome back. Looks like we have a generic equation. A plus B makes C. Can't get any more generic than that. 5 experiments. Looks like I'm varying the concentration of A and B, and I have the rates measured in molarity units per second. So let's find the order of the reaction with respect to A, B, and the overall order now. Remember, the overall order is the sum of the individual orders, folks. So let's erase these marks that I just put on here. All right, let's take a look. It looks like in the first and second experiment, A was constant. And it looks like I tripled B, right? And the rate did absolutely nothing. A was constant, B was tripled, the rate did nothing. So it looks like to me that B is zero order. No matter what I do to B will not affect the rate of the reaction. Okay? Now, what did you use for A's order? Well, let's take a look. It looks like in my second and third reaction, B was now held constant, and A was tripled, right? And what did the rate do here? It went from 3 times 10 to the negative third to 2.7 times 10 to the negative second. It went up 9 times. So when A was tripled, the rate went up 9 times. So you should see that A is second order in that case. Now, the overall order is the sum of the two. So A is second order, B is zero order. The sum of the two is second order overall. Looks like the rate simply depends upon the concentration of A. All right, let's write the rate law for this reaction, and we'll find the value of K. So R equals K, that's how I always begin, times A to the second power. And I guess we can include B here to the 0 power. In reality, we can just leave B off, because what's anything to the 0 power? That's right, it's equal to 1, and so it's never going to change it, but we'll leave it here. Let's solve for K now. So K is equal to R over A squared and B to the 0 power. And I'm going to leave B off on that one because it just reduces to 1. Now once again, I like to use the first experiment here because I have some nice data for A, B, and the rate. So it looks like the rate in the first experiment is 3.00 times 10 to the negative third molarity units per second. We're dividing it by the concentration of A, which is 0.10 molarity units squared. And remember, B is equal to 1. So it looks like one of these molarity units cancel out. So I have 1 over second molarity units remaining. And let's do the math now. We have 3 second EE to the negative third divided by 0.1 squared. And so I end up with a rate constant of 0.30, 1 over second molarity units. So now with that constant, we can find the value of A in the first experiment. So let's see if we can do that. Using my rate law, I can solve for A squared. Wouldn't that be equal to R over K? And sure, B to the 0 power, which is just going to cancel out. So if I want A by itself, I have to bring K and B over to the other side. Now this will be A squared. So we're going to need to square root this at the very end, kiddos. So let's plug in some numbers here. A squared equals the rate during that experiment, which is 9.00 times 10 to the negative third molarity units per second, divided by K, which is 0.30 second molarity units. True story? Oh, I messed up there. 0.30, messed up still. Second molarity units. All right, so let's see what we end up with here. 9 second EE to the negative third divided by 0.3 is equal to 0.03. Okay, And so we need to square root that, because remember, that's the concentration of A squared. So A, if we square root both sides, is equal to 0.17 molarity units during that experiment. So we can calculate the concentration of A during that experiment if we can find the rate law and the rate constant, which we did. Alrighty? All right, kiddos. We're going to move on to equilibrium in the next unit. You know what? We'll probably do a couple more of these practice problems for you. So we'll see you soon. Bye-bye.